Now, we're going to be interested in various kinds of changes that involve constraints. And we've seen one of these already in the previous video when we talked about bringing two things into thermal contact but keeping the volume constant. So one of the ways that we can impose a constraint is to have a constant volume. All right, now I'm going to go through the different things we can hold constant, and then I'll tell you what they're called. Another thing that we could have done is we could have a process that has a constant pressure or a constant temperature. All right, these are also constraints that we could impose upon a change process. A final kind of change that I'll talk about is, there are more than just these four, but we're going to talk some about adiabatic changes. These are changes that basically impose no heat exchange. So in other words, the incremental change in heat for an adiabatic process is equal to 0. All right, all of these others involve physical property changes that are held constant, and we're going to have a lot to say about all four of these in various future lessons. Now let me put a label on these so that we can use some special language. A change that involves a constant volume is called an isochoric change, based on Greek roots. A change that involves constant pressure is called an isobaric change. And you might recognize bar as being the same root as used in barometer. A barometer is something that measures pressure. So isobaric means same pressure or constant pressure. Constant temperature, this one will be also more familiar, we would call an isothermal change. That is, the temperature is not changing. Okay, now in the case of a constant volume, this means that V is staying the same throughout the process, theoretically. Likewise, a constant pressure process would be pressure is the same throughout the process, and temperature would be temperature is the same throughout the process. Now, these are particularly important to specify that they're throughout the process when we're talking about path functions. So in other words, these are going to be important when we want to measure something like the heat or the work that's involved in a change process. But if it's a state function that we're worrying about, if it's something like the internal energy or the change in internal energy, these will not care if it's actually the same throughout the process. All it will care is that it's the same at the beginning and the end of the process. All right, now I want to talk a little bit about PV diagrams. These are a special way we have of tracking these things. And I will also say that PV diagrams are especially useful when we're talking about reversible processes, because a reversible process allows us to actually specify a path graphically on a PV diagram. All right, so what is a PV diagram? Well, a PV diagram is one where we're going to draw a graph in which we graph pressure on the vertical axis and volume on the horizontal axis. And so each point in this graph is going to represent a separate pressure and volume, and these can change then throughout. So I could actually label this as point 1, and maybe I'd have another pressure volume point that would be here, that would be pressure and volume 2. Now, one reason that PV diagrams are useful is that they often enable us to determine other things too. For example, it is not uncommon to let the amount of substance in a system remain constant. We'll talk eventually about things where this changes, but at least for the first couple of modules, this is always going to be the case in our systems. So what that means is that we have an equation of state that relates the other variables, pressure, volume, and temperature. N is constant, so I'm going to put it sort of separate a little bit with a semicolon. But our equation of state, which I'll remind you looks something like this, will say that if I know where the pressure and volume is, I can always find the temperature. So for example, for an ideal gas, if I know the pressure and the volume, and I know that this is equal to nRT, but N is constant, then I can always solve for the temperature. It's just going to be PV divided by NR. So I can always determine what this is. So each of the points here in the pressure volume diagram, in the PV diagram, actually tells me about the entire state of the system. And that's why these things are useful.